Hello, welcome. This is a C4 video extending our knowledge on trig. Now in the first video, what we looked at disguised integration and integrating basic trigonometric functions, your sine, your cos and your tans. And I drew that table on the board if you remember back to that video. Okay, so we're going to be taking it a little bit further today. Obviously we're going to be coming up with some trig identities. Now don't worry too much. These identities basically are just a mimic of your C3 knowledge. Just combining. We're not going to be learning anything new. Well, hopefully you are, but I mean, we're not going to be learning any methods or identities, even though it is called that. So they're just extended identities that you already know. I'm assuming you do anyway. The C3 identities, there'll be a video on that if you don't get these, where these have come from. So hopefully, I'm assuming you've watched that video or you already know about the identities from C3. Now we're going to be using all the identities. We're going to be actually using the concumulation of the harder C2 identity and the C3 identities and putting them into one and coming up with a few new ones. What I like to do, just for our stress, when I put these, I'm not going to put them all up. I'm going to put them all up straight away actually, and then I'll work through each one and show you how we go to that. Personally, what I like to do, I know it wastes a bit of time, but this is my preference. Remember how they're formulated. So, I mean, to me it makes logical sense how they're formulated, but to you it might not. So, I mean, it depends what kind of person you are, really. I like to just think the way through them as well, so I remember the way. So if they ask me to show that question, which they could do, I'm not going to be stumped by just remembering the answer. I like to remember all of it, but I mean, the best people remember the method and the answer, so they can just the answer straight away. Whereas I like to work through it and waste time basically. But as I said, it's better to know the way through it as well than not know it at all. So if I remember the way through it, then I'm not going to forget it on the day. It's a lot harder to forget it, I think. Anyway, so formulatory identities. Now there's only a few. There's only 1, 2, 3, 4, 5. The last two you should know. The first one you should know. The second and the third one might be a little difficult, but I've got a method to go and formulate them. We'll go through them. So you should know your sine of 2x is equal to your 2 sine x cos x. These are the two that I'll go into. So it's your cos squared x equals, sorry, your 1, I always forget which round this is, plus cos 2x. And I'll explain why we have to do these in a minute, over 2. And then it's your sine squared x equals 1 take cos 2x over 2. And then obviously the other ones are you tan squared x equals your sec squared x take 1, and therefore your sec squared x equals your tan squared x plus 1. So these are two rearrangement of each other. I don't normally go through how you formulate that one because hopefully you should know that's just the simple addition formula. Putting a is in both into the sine addition formula, so you should know that. These two fairly, I mean that's just them. You don't need to know more than that. But actually, I will go through. We'll go through these two. I'll go through all of them actually. So your sine 2x, so your sine a plus or minus b, so this is your addition rule, is your sine a times your cos b plus or minus your sine b cos a. And then we just put a's into 2, so sine of x plus x is equal to sine x. Obviously you could put a here, cos x plus sine x cos x. So we've got our 2 sine x's and our 2 cos x's, so we can just simplify that down and say 2 sine x cos x. Because that's what I was saying, is 2 times sine x times 2 times cos x, well, we can just put 2 in front of them all. So that's how we get that formula there. Just make sure you can see that the pen's not going. I prefer this pen, but it's really running out of ink. So hopefully you can see how we formulate that one there. As I said, I prefer to. That's how when I think of it, I don't go straight to thinking of the formulae. Although for that one, for the sine 2xi, it's a lot easier just to think of that. But so we'll do the harder ones last. So the next one we're going to do is tan squared x plus sec squared x. So if I remember which way round this is, obviously no, actually, so it's a rearrangement of the answer. So it's 1 over cos squared x equals, obviously 1 equals your sine squared x plus your cos squared x. You divide all of that by cos squared x. So sine x squared over cos squared x plus cos squared x over cos squared x. Simplify that down. 1 over cos is your sec x. Sec squared x equals your sec x over sine x over cos x is your tan squared x plus your cos x over your cos x, which is 1. Obviously cos squared x over cos squared x is the same as cos x over cos x. So that's just a rearrangement of this. So I'll just move back to make sure you can actually see that. So don't trust the light. So hopefully you see how we've got them we've got them 3 equations there. 4 if you count that one as 2. Right. Now what we're going to do now is we're going to take it up a step. These two are a little bit more complicated. The reason for that is because we have to know when to apply this theorem, the cos 2x, really. Now for those of you that are looking at that, and because this is immediately what I thought as well, is I thought, well, why don't you just put, why don't you just put your 1 take your cos x squared, or 1 take your sin x squared for your cos squared x. Well, we could do, but that in C4 it's not going to be as easy as that, because that is, as I said, C2. And if they wanted to ask you that, they'd be ask you that in a C2 exam. Sorry, I thought you had something in mind. Just get a drink while I'm still alive. Okay, so I'll rub that other one off in a minute, so just set the camera on. Okay, so it's these two we're focusing on now, the ones that are left. Right, so your cos squared x and your sin squared x. Now, what we do here is we obviously start with the cos 2x. So, remind ourselves what cos 2x is, which is your cos squared x, take your sin squared x. Now what I'm going to do is I'm going to write the list of all the important ones, formulae that we need, that we should already know, to be able to combine them to get these equations. You should know, obviously, your cos squared x plus your sin squared x is equal to 1. I think that's about it, unless we come across any others. Obviously you should know your rules for integrating them, etc. So, what one are we going to start with? Well, obviously we're not going to combine these two together, by the way, sorry. Just yet. So, cos 2x equals is the same as saying your cos squared x. So if we start with the first one, cos 2x equals your cos squared x for your sin squared x, and then we can put one of these equations, so we can either rearrange that to get cos squared x, or rearrange this to get sin squared x. So you could do it either way, and obviously that would get you your 2 different equations. So what I'm going to do is put cos squared x in. Now we should know cos squared x is 1 take sin squared x. So you put 1 take sin squared x, take your sin x, your sin squared x, sorry, That's right, isn't it? Yeah. So that's why it's got a minus there, obviously. So then you've got your cos 2x, if we simplify this down, your cos 2x is equal to your 1 take 2 sine squared x. Move the add 2 sine squared x to both sides and take your cos 2x off both sides equals 1 take cos 2x. And then simplify it down, divide both sides by 2 sine squared x, right, equals, and you put this 1, you can either do half times cos 1 take 2x, sorry, or you could do what I'm going to do, which is 1 take cos 2x over 2. Okay, so that's how we get that one. How we get the other one, the cos squared x, instead of putting getting them both to sine squared x, we're going to change it both to cos squared x. So you know your cos 2x is equal to your cos squared x take sine squared x. Well, we want cos squared x in its own, so we're going to leave cos squared x in there. And we're going to change the sine squared x to your cos squared x, which is 1 take cos squared x. Simplify this down, so your cos 2x is equal to your cos squared x. Now you're taking away a 1, so it's minus 1. We take away a negative cos squared x, so it's adding cos squared x, don't forget. It's simple, people forget it. So your cos 2x then, damn it, if I can remember the 2, is equal to your 2 cos squared x. Take 1. Rearrange this obviously to get your cos 2 cos squared x in front, because we want your cos squared x to be the subject sort of thing. So if I move down, so your 2 cos squared x, add 1 to both sides, etc., and take away cos 2x. So that's 1 take cos, so 1 plus cos 2x, and then that's have to do with cos squared x equals 1 plus cos 2x over 2. Okay, that's how you formulate M2. Right, that might be a little bit much to take in, but as I said, all we're using was these two identities and mixing them together. I mean, you might have done that anyway by just thinking about it in C3. Thinking, oh, we can apply this. Well, you actually do that in C4, so C4 there. So well done if you thought of that. But as I said, that method makes sense to me to make me remind this. I don't think that they're not given to you in the formula book purely because you can work them out from what it's already given you. So the formula book won't miss anything out entirely. There'll be some related to it, so you have to manipulate the equations it gives you in the formula book to be able to use these, which it does give you cos squared x plus sine squared x, and you should know that one. And yeah, so you should be okay. I wouldn't worry about, if you can't remember that, that's a little bit, you know, it's not as easy as remembering cos squared x plus sine squared x equals 1. Then I'd quite recommend learning that method. But as I said, if you remember that, great, well done, you know. But it might ask you to prove it, and that's how you would prove it. Okay, just so I'm proving to you how we come up with them identities. So I'll just give you, just make sure you can see it, and I'll give you a second to copy it down while I sort of revive myself a little bit. And then we can crack on. What I'm going to do after this is I'm just going to do some questions out of exercise 8.3. Which is actually quite difficult for the people who are in my class, and then we're going to end the video and I'll just sum up the identities. So I'll just give you a minute to copy it down while I get in. Alright, so hopefully you've copied it down. Rub them off now. And then we're going to rewrite them at the top of the board, so when we're going through the questions you can have a go at some of them and manage it through. I mean, at the moment for me, the mark schemes for exercise 8.3 as I'm doing this now aren't up online for your C4 booklet, so I mean, as good as I am, I can't check these answers, but if they are wrong, I'll put something above my head now saying what an idiot, he got it wrong at 2 minutes 55 or whatnot, even though we're 18 minutes in, 15 minutes even, can't even read. So, let's rewrite all the identities. So, sine 2x equals your 2 sine x cos x. Your tan squared x equals your sec squared x. Take 1. And then your sec squared x, obviously, equals your tan squared x plus 1. Your cos squared x equals your 1 plus cos 2x over 2. And then your sine squared x equals your 1 take cos 2x over 2. So they're your identities. And then obviously you've got, I just write, I don't really think I need to write it down, but I will do, plus sine squared equals 1. I don't think you'll need any others for these questions, just let me double check. I think you will. I mean, obviously you'll need to know your integrating, standard integration rules for your basic trigonometric functions, which if you don't know, just revert to our earlier video. So, as I said, for those of you that don't have for those of you that have the booklet, it's at exercise 8.3, question page 33, and we're going to do question 1 to start with, because it sort of gets you in the mood back into thinking about the rules we had in the last video. So, first one, 1a, says integrate the following: your 2 sine squared x with respect to x. Doesn't say any limits or anything, so away we go. Now, the key thing to do when you've got 2 times something, take the 2 outside of the integral and rewrite it as so. So you've got your sine squared x with respect to x. Now we should know from the rules above, sine squared x is equal to, you 1 take cos squared, cos 2x over 2, sorry. So you 1 take cos 2x over 2. Now we haven't done anything, we haven't integrated anything yet. That comes now. So you could say, therefore, that is equal to, so remember, I'd like to put the 2 on the outside because we times it by 2. So your 1 over 2, you split that up if you want, which is I think what I'd recommend. So 1 over 2, you integrate that, what x would be. So that a half, is basically saying half times x to the 0, raise the power by 1 and divide it by that power, so it just becomes x over 2. You negative 2 cos x over 2, so your negative cos 2x becomes your your negative, so it's minus, because the sign stays the same when you integrate cos, but it changes when you differentiate it because it's opposite, remember. And then negative cos 2x would be negative sine 2x over 2. Because we're already over 2, it's negative sine 2x over 4, because we're dividing a half by 2, if that makes sense, which sort of doubles the denominator. But as I said, hopefully that's fairly simple. And then we're going to expand this out now. So that's your 2 times half of x, which is x. Take your 2 sine 2x over 4, and then that's your answer. So let me double check that. As I said, if that's wrong, the method's right, just the final bit for making any mistakes on that bit. Is that correct? Sorry, I don't know if I put 2 there. So just make sure that's right. Integrate your cos 2x, that's your cos 2x over 2. Yeah, that's right. So it shouldn't have been 2 sine 2x, it should be just negative 2. Oh, yeah, sorry, yeah. 2. I don't know when I'm thinking about this. So much that was right in the first place. So it's negative 2 sine 2x over 4. So that's your answer for 1A. As I said, if that's wrong then just let me know, but I really doubt it is. So that's 1A, hopefully done. Managed to copy that down, I hope. So we only really used one rule there, maybe two. What were the ones? Just pick another one. So question 3A is quite a good one actually, if we can find the booklet. I'm not going to go through the rest of them because, I'm not going to go through 3B because I think it's worded a bit funny and I don't want to confuse you, because the way I think about 3B is a little bit confusing. So I'm just going to leave it at 3A. Skip out 2. 1B I did leave out, but I can do it. If you want me to do 1B for the people in my class, or do some more questions, just let me know. But I'm trying to keep it fairly neat. Okay, so y equals 3 cos x. It tells us, and it says sketch the function. Now I wouldn't read any more than when it says sketch, because obviously it wants you to perform sketch. Well, I would actually. It says between the curve x equals 0 and x equals pi over 2. Now obviously it tells you in radians. And if it's between 0 and pi over 2, it's saying 0 and 90, which is essentially half a quarter of an oscillation, because oscillation 360, 2 pi 180, 2 pi 90. That's the way I think about it. Obviously real logic behind that. Now how do we know what this curve looks like? Now you should all know what y equals cos x looks like, but what does the curve of y equals 3 cos x? Well, this is the same as saying y equals f of 3. 3f of x, sorry. Rewrite that. Which means it's because it's outside the x, it's not timesing the x values by 3. It's not dividing the x values by 3, it's timesing the amplitude of the y values by 3. So, as it's between x and 2, what I sketch yourself is a nice graph. So a short negative bit, because we're not going to be interested in the negative bit. So that's your x. Sorry, my thing is quite bad. Starts at 1 normally, but because times the y value by 3, it has a maximum of 3 and a minimum value of negative 3. Obviously yours will be a lot neater than mine. It sort of does that. Okay, so then you've got your, so it should be negative 3 by the way. If that makes more sense. So it's sort of, so 2 pi is over here, but it's obviously it doesn't sketch it between 0. You can sketch it what you want, but generally we're interested in this bit here because this is where it touches 90 or pi over 2 as it asks you, and it wants you to find this bit. So basically what it's saying is ask this bit, because it's saying between x is 0 and x equals pi over 2, and this is x equals pi over 2. Sorry, that should have gone through 90. Pi over 2. So it's asking you to find this value of the area. So it's the area, right? So how would we do that? Now, obviously, to find the area of curves, we integrate them, and basically the pi over 2 and the 0 is the two limits. So if we rewrite the equation, so pi over 2, 0 as the limits, and it's asking us to differentiate 3 cos x with respect to x. Basically, that's what the question is asking. All this working out was just to get to this bit here. Okay, so what I like to do is not worry about the limits. I like to do a separate thing. So basically I'm just integrating 3 cos x. So we'd have to worry about the limits, because obviously we're going to have to integrate this and then input the pi over 2 and 0 and take them away from each other. So that's what I like to do there. So obviously that equals your cos x. If you integrate that, you get positive sine x. So it's just 3 sine x. Which is what I did. Well, I didn't do what I should have done. So that's what that is. Because obviously that's the same as saying 3 times the integral of cos x, which is just sine x, because we're integrating, not differentiating, remember, that's why it doesn't change the sign. And then that's our integrated value, so then we just put in our, back into our equation, so just rewrite the original equation, so pi over 2, 3 cos x, sorry if my hand's not, the work isn't neat, just trying to keep it on the side for you, and then we just put pi over 2 into the equation, take away from 0, so 3 times cos of pi on 2. Take 3 times cos of 0. Even if it is 0 and you think, oh, I'll just leave it out, always put it in, because, you know, for some of the functions it is 1, which it is for cos. So if you kind of left it out because you just thought, oh, it's times by 3 cos of 0 is 0, it's actually 1. Because you can take solace from the fact at 0 here, it is 1. Well, it's 3 here, but on another look at it, it'd be 1. So what's that essentially saying is 3 times cos of pi over 2. Take 1. So if you do that, 3 times the cos of pi on 2. Sorry, calculators get the better of me sometimes. So that's 0. Take positive cos x, which is cos of 0, which is 1. Take 3 equals minus 3. So minus 3 should be your answer. So hopefully that makes some kind of sense. As I said, I apologise for my scruffy writing there, but I was just to try and emphasise the point a little bit more by making it messy. I just come up with an excuse, to be honest. So I think I'll leave it there actually in terms of doing the questions. I think that's the sort of main gist of it, really. The rest goes on just emphasises that, really. So, as I said, hopefully it's been intuitive. Just going to finish off now by, just... So I've already wrote them there. Actually, I was going to write the identities back in, but I've already done that. So I'll just rub that out. Thanks for watching, and thanks for surviving, if you managed. And we'll see you in the next video, which will be integrating substitution by parts, if that makes sense. So we'll see you in the next video.